Okay, to finish up the energy unit, we're going to look back at potential energy, gravitational potential energy. And we said PE equals mgh. And where is that true? It turns out it's only true near the surface of the Earth. Okay, because this g here only equals 9.8, very near the surface of the Earth. It's going to be a little more complicated, say if we take something from far out in orbit and it falls towards Earth, it's losing potential energy, gaining kinetic energy, but we can't use this mgh equation anymore. The equation we're going to use is PE equals minus g m1 m2 over r, which looks a lot like the force of gravity equation. It's just r in the bottom instead of r squared. Now, one thing to note is that PE at r equals infinity equals something, okay? Now, if I put infinity on the bottom, I put a gigantic number on the bottom of a fraction, that fraction is going to be very, very small, and if I put infinity on the bottom, I get 0. So the potential energy when r equals infinity equals 0. And then at all other locations, actually the potential energy is negative. Okay, I've mentioned to some of you before that you can set where your 0 is going to be. If I was on a second floor, I wouldn't probably and I'm measuring the potential energy of a book I'm holding up, I wouldn't measure the distance all the way down to the ground floor. I would be setting 0 at the floor that I'm standing on, and then anything below that would actually have a negative potential energy. Same thing here, we're setting our 0 infinitely far away, and anything closer than that is going to be negative. So here's an example. A satellite with a mass of 200 kilograms falls in orbit 200,000 meters above the Earth's surface, and I want to know its velocity when it reaches the surface of the Earth. So I'm going to draw a little picture of this. Okay, here's the Earth. Now I know the radius of the Earth, this distance right here, is 6.4 times 10 to the 6. That's given right here in the problem. And then this thing is starting out here 200,000 meters farther away. So we're going to call this point A where it starts out, and this point B where it ends up. So at point A, it's going to have PE equals negative G M1 M2 over R. Okay? Now, if you remember, the G is 6.67 times 10 to the minus 11th. M1 is the mass of the Earth, 6 times 10 to the 24th. Times the mass of the satellite, which is 200. Now we have to divide that by R. R stands for the distance between the centers, so it's the 6.4 times 10 to the 6th plus 200,000. So 6.4 times 10 to the 6th plus 200,000. And that gives me a potential energy of negative 1.21 times 10 to the 10th joules. And we're going to assume it starts from rest there. So its kinetic energy is 0. So our E total is negative 1.21 times 10 to the 10th joules. Then we're going to look at point B. All right, the PE there is going to be negative G M1 M2 over R minus 6.67 times 10 to the minus 11th times 6 times 10 to the 24th times 200 divided by, and now the R has changed to just the 6.4 times 10 to the 6th. And that's going to give you a value of negative 1.25 times 10 to the 10th joules. KE is going to be 1/2 mv squared. I'm going to use the mass of the satellite because that's the thing that's moving. So 1/2 times 200 times v squared, or 100 v squared. And that gives me an E total of 100 v squared plus negative 1.25 times 10 to the 10th joules. Then setting them equal to each other, that gives me negative 1.21 times 10 to the 10th equals 100 v squared minus 1.25 times 10 to the 10th. So I'm going to add the 1.25 times 10 to the 10th to both sides, and I'm going to get 4 times 10 to the 8th is 100 v squared. V squared equals 4 times 10 to the 6th. It's going to give me V is 2 times 10 to the 3rd, or 2,000 meters per second. So when that thing falls from orbit, it's going to hit the Earth with a speed of 2,000 meters per second. This next question talks about escape velocity. The escape velocity is something that it must have to completely leave the gravitational pull of the planet. So we're going to do something like that here. So we're going to say that this object starts, and remember the radius of the Earth is 6.4 times 10 to the 6th. We have an object, say, of mass m on the surface, and we want to launch it so it gets completely away. So this is going to be point A, and this is going to be point B. And we're going to write down, remember the mass of the Earth is 6 times 10 to the 24th. So there's the data we're going to need. Now, point B, to completely leave the gravitational pull, no matter how far away I get, there's still some gravitational pull. It gets weaker and weaker and weaker. But to completely leave it, we have to get to a distance of infinity. All right? And we just have to get there. We don't have to be moving very fast when we get there. So we're going to say that our minimum velocity there is going to be a velocity of 0. And that'll give us the minimum velocity back here at point A in order to reach that point. Okay, so at point A, we have PE is negative Gm1 m2 over r. It's negative 6.67 times 10 to the minus 11th times m1, mass of the Earth, 6 times 10 to the 24th. I don't know the mass of the object, so I'm just going to call it m, divided by r, 6.4 times 10 to the 6th. When I do that, I'll get a value of negative 6.25 times 10 to the 7th m. And its kinetic energy there, I don't know. I'm trying to find out what velocity it has to have there. So I'm going to do 1/2 mv squared. I don't know m either, so that's the most I can do with it. So my E total is going to be 1/2 mv squared minus 6.25 times 10 to the 7th m. Now, when I get out to infinity at point B, the PE is going to be minus Gm1 m2 over r. But remember, r is infinity. If I divide by infinity, I get 0, so the potential energy is 0. The kinetic energy is also going to equal 0 because the velocity is 0 out there. So my E total here is going to be 0. Then setting my E totals equal to each other, and I get 0 equals 1/2 mv squared minus 6.25 times 10 to the 7th m. Now I could add that to the other side. 6.25 times 10 to the 7th m is 1/2 mv squared. M's can cancel. I'm going to multiply both sides by 2. So that's going to give me 13.5 5 times 10 to the 7th is v squared. And then our velocity is going to be 11,619 meters per second. So that's the escape velocity for Earth. If I was to fire something from Earth at that speed, it would never come back. It would reach infinitely far away.